Hello students, as discussed in the last slide in the last module that in this module we are going to combine both the match filter based approach and the serial search active correlator based serial search architecture to see whether we can get the advantage of both of them in a new one, and that one we call a two-step mechanism that we will be discussing today. So, fundamentally we are going to club the match filter based passive correlator architecture with the active correlator based serial search architecture, and we understand that match filter gives us a very fast acquisition at the cost of high probability of false alarm and high complexity, and on the contrast serial search mechanism gives us very high detection probability, lowering the false alarm and at the cost of long acquisition time. Okay. So, target is what? Final target is to get the high detection probability, low false alarm with reasonable time of acquisition. Okay. So, here we are, the mechanism is called a two-step synchronization mechanism, and we understand that the communication in the push to talk network on which all these schemes we are continuously discussing, the communication there is of burst type. We call it a sporadic characteristics of the communication, and rapid and accurate techniques are required really to facilitate the desynchronization on each and every transmission packet. So, that is the main motivation of this third form, where actually fast acquisition is required, also very good acquisition, I mean accurate acquisition is also will be the most important part. And this two-level synchronization mechanism of FHSS approaches of it was first analyzed by Professor Epaport and Schilling, and this is a basically combination of this match filter plus the serial search technique. Let us see the next slide to understand what exactly is going on here. But remember, here also we will consider that there are capital H number of the Hop frequencies involved in the synchronization sequence. We will send a leader for it, the way we sent the leader for the match filter as well as the serial search. And there are two stages. The first stage is having one set of the threshold called the gamma Th1, and second stage uses another stage of the threshold which call it gamma Th2. And remember, the searching is also divided into these two steps. The first step finds suppose P capital P number of the searches, capital P number of the tones out of the capital H to be searched, and the remaining capital A number of the tones will be searched in the second step, such that capital P plus capital A, the number of the tones searched by the stage 1 and the number of the tones searched by the stage 2 totally means combinedly gives the total number of the tones over which the hopping is going on. So, this is the block diagram of that two-step architecture. As I said, the first stage ends here. Okay. The second stage consists of this, so stage 1 and stage 2. The first stage consists of a match filter. So, stage 1 is passive correlator based architecture, and stage 2 is active correlator based architecture consisting of. And as I told that threshold value also of the first stage and second stages are not same, they are different. The philosophy is what whenever the signal is received here, the match filter starts working. So, in the match filter we are having actually say its task is to find out say capital P number of the tones out of your capital H number of the tones. So, out of capital H, it is targeted to find out the capital P number of the tones. So, you need not to actually build up a match filter architecture here, where the number of the stages, parallel stages involved will be capital H. You need to put here now the very less number of the parallel chains of the match filters, which is equal to capital P. But philosophy is that if the match filter output for all those capital P number of the searches, he will search maybe actually for over all the capital P, and out of this, if we can find actually for all the capital P number of the stages, there is a sufficient number of amount of the statistics such that the statistics is crossing the predefined gamma value or the threshold value, then there is a indication that match filter is giving an indication that there is a chance of getting a synchronized tones and synchronized tones within this received block. So, the received block is fed to the match filter, and see received block is also fed to the active correlator bank of correlators, but active correlator bank never starts working without getting a trigger input from the match filter output. So, once match filter finds that the output of this threshold comparator at the output of the match filter is really high, that means the match filter output is crossing the predefined threshold, then actually it means that there is a chance that if you search over the same period, over the same set of the incoming chips, there is a chance that you can be able to find out the synchronization point. Then the active correlator is activated, and here is we are having a bank of active correlators, and any one of that bank of active correlator is activated. Suppose I have capital C number of the correlators here. So, out of capital C, any one of the correlators will be activated by the output of this stage 1, and he will try to do the serial search, the mechanism that we have discussed in the previous one, and his task is now to find out the remaining capital A number of the tones. I mean finding out the remaining capital A number of the tones, and this search actually is a very long lengthy process, and serially it keeps on searching, and once he is searching, we understand that the output of the every step, output of the every tone when it is searching, it should be sufficiently large. It should be most of the cases, if it is actually well tuned, then only the output statistics Z will be high, and then any one of these bank of the threshold two comparators are having the second level of the thresholds, the output will be high. Now, if the output is high, then the control will give actually based on where you are in, and based on that control will either declare that the sync is completely locked if it can find all the capital A position, or if it is not, then he will readjust the clock slowly such that it can get aligned with that capital A number of the path. So, the situation is such that I understand that if serial search over all capital H number of the tones needs to be done, then it is a very lengthy process that the correlator cannot do, because it will take huge time. To reduce the time, the partial search is performed by the match filter by parallelizing the whole architecture, and by parallelizing each, we choose actually efficiently those capital P number of the tones, the presence of whom also confirms that there is a chance that this is a chunk of, within this chunk of the bits, the synchronization points will be able to be searched by the active correlators. Then only we trigger the active correlators. Now, remember one thing, if my active correlator does not find actually the sufficient amount of the Z value, the test statistics value, then what he will do, he will actually declare that he could not find, and he will actually be pooled, he will be drawn in the pool of the correlators, where actually match filter will assign him some job at certain other point of time, and say maybe the second correlator, some other correlator may be assigned the same job by the match filter. but whether match filter has the time to assign the job to the second or the third correlator, that depends upon remaining time of the total acquisition time within which you need to complete the search. So, and if the situation is such that all the correlators are busy at a particular point of time, when the match filter has found some kind of the pre-sync message that he could actually get by comparing his output with this gamma th1, when all the correlators are busy, at that moment, even if actually match filter is trying to say that there is a chance to find out some synchronization point within this capital NC, within this set of the received chips, the correlator, none of the correlators will take the input, none of the correlators will take the job, and in such situation that request is totally discarded. So, see what we have done in this combined architecture is acquisition, huge acquisition time required by the serial active correlators is reduced, and reduced by a great extent by partially implementing the match filter. So, the total H number of the tones we have divided into P plus A. The P number of the tones will be searched by match filter, and A number of the tones will be searched by the remaining active correlators. The P is chosen in such a way that for those tones they may be scattered, they are not required to be sequential one, they may be actually some rapid number of the tones, but if that random tones out of capital H match filter is able to find out, that will be done at very fast speed, but with possibility that the probability of the false alarm is also high, and that is why actually next stage the serial search is very essential. And for all those remaining one, actually if you are doing, I understand that for this capital A time, for capital A number of the tones, the serial search will be done in such a way that the detection probability will be very high. Here the false alarm probability is high, detection probability is less, but here the detection probability is very high. So, in average it will be a balanced detection probability for A plus P number of the tones, actually guaranteed by the active correlators, if it can find the capital A number of the tones. At the same time, actually the time, the higher time that is consumed by the serial architecture, I mean the serial active serial search active correlator based architecture, that is counterbalanced by the very fast acquisition that is occurred to avail this P number of the tones by the match filter. So, one way actually the detection probability is getting balanced by the serial active correlator, another way the acquisition time is taken care of by the match filter. So, combinedly it is expected that with a low noise situation you will be able to detect both the P and A number of the tones, and with a reasonable time of the acquisition and with a reasonable time of acquisition and a satisfactory level of the detection probability. So, that is the gain of this whole architecture, where the disadvantages of both the techniques are nicely combined to get a pretty good and satisfactory performance of the detection probability as well as the acquisition time. So, this two-step mechanism proposed by Professor Rappaport and Schilling, they are very popular and they are widely used also in the PDT network. But remember, as we have incorporated both the match filter as well as the active bank of active correlator architecture, complexity wise actually you have not gained much, because match filter, anyway match filter is a hardware complex, hardware intense, and this guy is also having several other architectures and hardware components associated with it. So, we could not actually do much over the hardware complexity, but with that is a cost function of this architecture, but with respect to that we have gained a lot in the performance in terms of detection as well as the acquisition. Both has been improved by combining the earlier two mechanisms. So, that is the plus point of this two-step one. In this slide the same stuff is explained, and remember at the end of this capital H number of the hops, if the active correlator has detected enough of the hops, its output will exceed, as I told, and the second threshold indicating the sync lock has been achieved. But if it does not exceed the second threshold, then the correlator is made available to the pool and for a new assignment to be done by the match filter. And if there is no active correlator available when the match filter output has detected some part of the capital P number of the tones, then actually the whole notification will be completely ignored, because nobody is free to take the charge or take the assignment to find the remaining capital A number of the tones. And so you have a P number of the passive match filters in the first stage and capital A number of the active correlators in the second stage. How will you divide this capital P versus capital A? That is the design choice, and it will actually largely affect the acquisition time constraint within which you are trying to complete the design and the detection probability. What is the minimum required detection probability of yours? Now, relatively low reliability but the fast performance of this match filter we have used to present through the possible code offsets before the time consuming, but high reliability active correlators are coming next, deployed to improve the detection probability, as I have already told. But hardware intense and hardware light, that are also getting combined. And effect of the interfering signals and jamming tones essentially will be of twofold. See, to increase the number of the false detection, actually that jammer can increase the false detection probability in the first step of the two-step process, and if it is really high, then it increases the load of the correlators in the second step, because it increases the blocking probability also. And however, this increases in the probability of the correctly detecting the beginning of a correct synchronization sequence also is possible because of this whole architecture. We will see actually in the next few slides how this blocking probability is coming into picture if we are having a large number of the false detection coming from the first stage to the next. The false alarm and the misdetection probabilities, the expression we have seen earlier also, they are given repeated once again, and where actually this capital H will be equal to P and this gamma will be given by your gamma Th1 by the total noise power for the first step. For the second step, capital H will be equal to capital A, because A is the number of the step tones over which you are searching, and gamma will be basically gamma Th2 by the normalized total noise power. Probability of the missed synchronization on a single pass through the synchronization process will be given by this expression. This is a newly developed one, where we consider that there is a total misdetection. So, total misdetection means, or missynchronization means, it should be a combination of the first stage plus the second stage. So, this is the first stage misdetection and this is the second stage misdetection. BCA, this is the Erlang B formula of the blocking probability it is talking about, and how this Erlang B formula. So, the total misdetection is a function of not only the misdetection of the first stage and the second stage, it is also a function of the blocking probability coming into picture, where this blocking probability or the Erlang B formula is given by this. And remember, with where this A, the value of this A is given by the false alarm of the stage number 1 and multiplied by the number of the tones assigned to the stage 2. And why this Erlang B formula is coming here is because it is basically a formula that reflects the likelihood that a call will be blocked in a normal telephone network, and the call attempts to arrive according to if we consider that the call is attending, it is arriving as a random process and its arrival process is given by a Poisson distribution, and it is an indication that here it is an indication that as an indication of whether our active correlator is available or that active correlator is not available. It has some similarity with the telephone line. Actually, the call is dropped if your line is not free, kind of. So here actually the request from the match filter is getting dropped if your correlators are, none of the correlators are free. In the formula, this blocking of formula, Erlang blocking formula, the C represents the number of the processing assets that are available. You mean the number of the active correlators available in the second stage, and the A, this guy, he is representing the number of the, what is the task performed, that it represents the rate at which each of the correlators are given a typical task to perform. So basically we can map the normal blocking probability of telephone network can be mapped here with the availability of a correlator in the second stage and the job assigned to each of them. Based on that, whether there is a chance that even if actually the match filter output or the stage number 1 is delivering something or requesting something to proceed, the second stage is discarding that effect and discarding that request. That is why actually you are seeing that the detection probability as well as the no sync misdetection is a function of this blocking also. So that is why it is like this. We have reproduced the formula once again. We will try to plot this now in the second slide. We will try to plot this as a function with the several values of the C, and let us see if I plot it, and this is a blocking probability. Remember, this blocking probability is, it is a function of this C, right, the number of the asset available in the stage 2 or the active correlator, number of the active correlators are available. And so we can find a very nice result that if the value of the C is less than 7, the blocking error probability will turn up, and this is because that blocking probability will be increasing with as the SNR increases. But if you cross the number of the correlators greater than equal to 7, then this typical characteristics totally disappear. And let us see how does it go. In the next slide, let us see the blocking probability. Actually, it is a no sync. The no sync or the misdetection probability actually it improves if I keep on increasing the value of the correlators in the active stage, but it will always also goes up actually if you increase the SNR, because the blocking probability Erlang B formula, the Erlang formula that is there, if you look inside that, we see that you will see that if the SNR is increasing, the blocking probability is slowly increasing, and if the blocking probability is increasing, so hence the misdetection again will be increasing. So with the increment of the SNR, first the misdetection will be decreasing, and then based on a typical value of the C and the point after a certain point, that varies also on the number of the, based on the number of the correlators utilized for the active stage, the blocking probability suddenly starts increasing with the SNR, and hence the SNR, hence the detection probability also decreases and the misdetection increases slowly. And beyond 7, actually at this kind of the graph, this issue is not there at all. And though the false alarm probability, it varies with the signal to noise ratio a lot. The threshold values we can adjust for these curves to make the probability of false alarm approximately 10 to the power minus 5 at 0 dB SNR for this kind of the cases. Now, if I try to understand what is a false alarm of the two steps jointly going on. So, false alarm probability of joint false alarm probability at the end should be given by the false alarm probability of the stage 1, false alarm probability of stage 2, and also the allowing the number of the times actually the second stage or the correlator serial correlator stage is running actually. So, 1 minus the blocking probability. And whereas for the serial search mechanism alone, the several passes through the sync frequencies could and should be attempted before declaring the code lock, which is not possible really for your two-stage technique, because if you are trying to see the actual serial search mechanism, we take multiple iterations over the multiple dwell time before declaring there is a sync lock. Here if you try to do that, you cannot do it alone over the serial search methods, over the serial search portion. You have to do it over the whole architecture. So we do not prefer to go that way. Multiple attempts here you can make of, but you have to actually then run here on the first stage as well as in the second stage. And in such a situation, you have to then the whole false alarm probability will be increased, and also the detection probability and the time acquisition of the acquisition, everything will be under time. So probability that there is no sync acquired, that will be finally 1 by the minus of PHK of m, where PHK we understand the probability of a hit on each and every individual pass. So if I am going over the small m passes, so it will be raised to the power m, and no sync means that there is no detection at all happening, that will be a 1 minus the total one. Here is the expression for the PHK, the hit for each and every search, and no sync hence actually finally will be given by this expression we have seen earlier. The total time acquired now, which is the most important part, for which we did all this, we realize that the detection probability has increased, but we have not understood yet how far actually we are good in acquisition time. The acquisition time, do you remember we saw a small m here in the acquisition time of the serial search. Now that m is vanished because we understand that we are not really going to repeat it over the m number of the period, and there is the acquisition time which will be ending up with. If I compare the active and the passive search techniques, the mean acquisition time here will be a function of your this number of the hopping. If your hopping is more, then your active serial search techniques, they will keep on actually increasing the mean acquisition time, that is obvious, and passive is far better compared to that, because passive is parallelly implementing all that. So there is no large increment over the, if your h is increasing, that is obvious, we understand now. And now if I try to compare the serial search and the match filter based mean acquisition times that I have shown in the last slide, we prefer the passive approach to go ahead if it is an acquisition time based. And of two level approaches, if I am trying to see for the PTT communications, then here we are. So A is equal to 20 means in the serial search process, the 20 number of the tones are remaining to search, 10 number of the tones remaining to search, 5 number of the tones remaining to search, and 1 number of the tone remaining to search. So if your P is increased, definitely if your number of the with a fixed number of a P, let us first understand, with a fixed number of P say equal to 6 or something like that, it should be 5. This 5 is for here, this number 5 is for this point, 10 is for this point, 15 is here, hence, and 20 is here. So say first stage, the number of the tones that your match filter is searching is equal to 5. If that is the situation, then if I am keeping only single tone to be searched in the serial active search technique, then your acquisition time is around 0.25 second, and more actually you are increasing the number of the tones to be searched by the serial search technique, keeping the capital P value, the number of the tones to be searched by match filter fixed, hence you see the acquisition time is increasing. Okay. And if I do some structure like this, that we have increased the P up to this, and then only one total, suppose 6 numbers of stuff needs to be done, or total say 10 number of the tones needs to be searched. So you can actually increase it to be 7 or 8, and then you do it by 1, or you increase it by 9 and then you do it by 1. So you can avail it very low amount of the acquisition time. So, how we are going to choose the segregation of P and A? It is not only a function of your acquisition time only, it is also there is a hardware complexity involved, and its restriction from that point is also needs to be done, and the detection probability, what is the target detection probability of yours. So, there is a crucial choice between these two tone distribution between the two stage architecture. So, with that we are ending with this frequency hopping spectrum code acquisition techniques. We have learned 3 different techniques. First one was the match filter based, giving us a very fast acquisition and very at a cost of very high probability of false alarm, detection probability is less. We then learned a serial search active correlator based mechanism, where we have got a very high detection probability at the cost of very low, very large acquisition time, which is not acceptable. Then we have learned to combine both the techniques, which is a 2-step technique, where we have divided the search mechanism between these two, and we could improve the acquisition time to a reasonable one, and detection probability also was improved by taking care of the, it is a balanced actually, some part balanced the some section balanced the detection probability and some section balanced the acquisition. So, as a whole the detection probability as well as acquisition was improved. That is all about the code acquisition mechanism of the frequency hopping spectrum communication. Next module we will discuss about the frequency hopping code tracking.